All right. Thanks for coming to today's lecture. Then this is the very last lecture of this subject in this semester. And then in the next lecture, we will have our presentation. So the next lecture will be our presentation day. Then I can't wait for that. Every semester, the presentation day is most a wonderful time for this subject. So can't wait for that. And hopefully all of you have prepared for the presentation already. All right, so today is mainly about subject review. And first we will talk about the quiz 2. And then second, we will talk about the project, especially for the presentation. Then we will talk a little bit about the final exam. I think this is I think most of you care about that. And then after that, we will give a subject overview. It's a complete overview of what we have in this semester. And then and after that, if you still have some questions, you can ask me. And also after the presentation day, I will arrange 2 consultation time. So I will arrange 2 days for the consultation. But for my experience in the previous semesters, it is better to organize the consultation time a bit later, maybe quite close, maybe better to close to the final exam date. Then you will get more questions to ask. All right, so at the beginning, let's talk about the sorry, wait a minute. Let's talk about quiz 2 first. I've already released the mark on quiz 2 on the UTS Online. So double check with your mark. If you have some questions on your mark, or if you think I made something wrong, please send me an email. All right, please send me an email. I will double check together with you. All right, so in quiz 2, there are 2 questions. There are 2 questions in it. And in the first question, it is about triangulation. It is about triangulation for the stereo camera. I found some issues. I found some issues that wait a minute. I found some issues that the equation. Most of you have used the correct equation, which is first calculate z from that equation, and second calculate x from z and that equation, and then you can calculate y as well. All right, but the thing is, I found some issues about the calculating the xl, yl, xr, and yr. Please look at this figure. As I mentioned before, the xl and xr here are with respect to the origin of the principal point. So it is not the original UV values. It is not the original UV values. So which means if you have the UV values for the features on the 2 images, the first thing is you need to delete the principal point. Then you can get the XL, XR, YL, and YR, which you can use in the following equations. All right, so I found some of the students, they didn't do this. They didn't do this. Then the result is, if you didn't do that, you may have a correct Z on the value, but definitely the meaning is not correct. So you have a correct value of Z, which is 1.2 meter. But the thing is, when you calculate X, then it is different, right? And when you calculate Y, it's different as well. So if you calculate the XL as the original UV value, then which means the X and Y, they are wrong. All right, so for doing the triangulation, the first thing is find the correct equations. Right, so the correct equations are here. And do remember, always calculate Z first. Always calculate Z first from XL and XR. So in this case, the XL, XR are not 0, but the YL and YR, they are 0. Right, so in this case, you need to use this equation to calculate Z. But if it is the other way around, so if XL and XR are 0, but YL and YR are not, then in this case, you need to use a similar equation that with respect to YL and YR. And that's it. All right, so first, we need to calculate Z. Calculate Z. And then after you calculate Z, then you calculate X and Y. All right. And before you applying those three equations, the very important thing is you need to change the origin from the top left of the image to the principal point, and which means if you have the original UV values of the left and of the features on the left and right images, then you need to delete the principal point out from the original UV values. Then you have your XL, YL, XR, and YR, and then use them to those three equations. All right. So this is the most questions or issues I found in quiz in question 1 in quiz 2. And another issue I found is that I gave a translation of the two camera centers, which is 0.15, 0.150, and 0. And someone doesn't know what is the baseline of that. The baseline is a distance. Is a distance between the two camera centers, and which means the baseline in this case is the norm of that translation between the two camera centers, and that is 0.15. Again, baseline is a scalar, which means baseline is a number instead of a vector. All right, and then if I'm directly giving you the baseline, then just use it. If I'm giving you a relative translation from the left camera to the right camera center, then you need to calculate the norm of the translation, which is the length of the translation, and that will be the baseline. All right, so those are the two questions I found, two issues I found for quiz 1. So the question 1 in quiz 2. All right, then the question 2. In question 2, there are 3 sub-questions. The first one, I think it is quite easy, right? If you find the correct equation, then you can get the correct answer. All right, and the first thing is you need to identify if the system is discrete or continuous, because the solutions are different. Right? And suppose you identify that the system is discrete, and then you choose the right solution equation for the system. And the next thing is you replace the equation by the actual A and B, something like this. And do remember, you don't have to calculate this number in, because sometimes it's quite hard to do that. So you don't have to do that. You just write something like that, and that is fine. I find some of the answers, they did the wrong one. They did the wrong one by calculating this power into the matrix. But I didn't reduce any of the mark. But what I mean is you don't have to calculate in. All right, so that is the first question in question 2. I don't think there are too many issues on this sub question, and the second question in question 2, the second sub question in question 2, is about stability, the stability. All right, I thought most of the students, they can get the correct eigenvalue of the A matrix, but I still find a few students, they get the wrong answer. I do suggest if you have similar questions in your final exam, then because it is open, it is open exam, it's open book exam. So which means you can use MATLAB. I'm quite happy if you use MATLAB in the final exam. What I mean is you need to write how you can calculate the eigenvalues. You can't do this directly by using MATLAB, but the thing is you can use MATLAB to double check if the eigenvalues you calculate are correct or not. Right, suppose the A is your matrix, just use EIG A, then you can get the eigenvalues of A. And then you can double check the values of the eigenvalues you calculated and the MATLAB calculated. Then to double check if it's correct or not. All right, so that's the first thing I got. To double check if the eigenvalues you calculated are correct, then you can double check it with the MATLAB functions. All right, and another issue I found is that for some of the students, they use the wrong criteria about the stability. Although the answers are the same, but they use a wrong criteria for checking the stability. And again, the first thing is you need to check the system is continuous or discrete, right? And in this question, it is quite obvious it is discrete system, discrete time system. Then the criteria for the stability for continuous and discrete time system, they are different. They're different. So for the continuous time system, if all the eigenvalues are negative or have negative real powers, then which means it is continuous. But in the discrete time system, the criteria are different. So if the system, if all the eigenvalues are between -1 and 1, then it is stable. Otherwise, it's not. All right. So apply the correct criteria when you give the answer. All right. So if you have the same question in the in the final exam, so please write the criteria that you used, not only a conclusion. All right. So suppose in this case, you calculate the eigenvalues of A are 9 and 1, and then you can't directly give a conclusion. You can't directly give a conclusion to say that it is unstable or not. So please write a sentence to say it is unstable because all the eigenvalues are larger than 1, something like that. All right. All right. Or you directly write the criteria. So if the eigenvalues are between -1 and 1, then it is stable. So in this case, it is not stable. All right. So answering this question, first calculate the eigenvalues of A. Then second, write the right criteria. And third, give a conclusion if it is stable or not. All right. So that is the second sub-question of question 2. And question 2C, the second sub-question of question 2. It is about controllability. I think most of you give a very correct answer. So the first thing is you need to calculate the controllability matrix, which is CT. Then you have to calculate this controllability matrix CT correctly And then after that, you can check the control. You can check the if the matrix is full rank or not, and to give a conclusion on if this is controllable or not. Again, you need to write the criteria before you give the conclusion. And also, here's a reminder. So for the controllability for continuous and discrete time system, they are the same. The criteria are the same, but for the stability they are different. So do remember on that. And so in this case, to check if it is full rank or not, then there are two ways, right? One is the mathematical way. You calculate the determinant. If the determinant is equal to 0, then which means it is not full rank. Then which means it is not stable. No, sorry, it's not controllable, right? And another way is the intuitive way. So if you times 2 on the second row, and then it is equal to the first row, right? Then which means you can present the first row by a linear function of the second row, and which means it is not full rank, and then it is not controllable. All right, so any questions on quiz 2? Just unmute yourself to ask, or you can put your question to the chat. All right, so if all good, then let's move to the next one. And then again, so double check your marks on quiz 2 together. If you have any questions or you think I did something wrong on the marking, then please send me an email to let me know. It is 15. It is 15. So it is a mistake. I'm going to change that. So totally, quiz 2 is 15 marks. All right. So I'll change that. All right. All right. So that is quiz 2. And also, if you still have some questions, then you can post it to the chat. Then after the lecture, and then I will answer one by one. All right, so this is for the feedback on quiz 2. Then another thing is before the review. Yeah, before the review, let's talk briefly about the group project. All right, so the deadline for the code and for the video has been extended to this Sunday. So send it to me anytime before Monday, and that is fine. But the thing is, I can't make any further extension on that, as I mentioned, because on next Tuesday, Tuesday morning we will have our presentation day, and it is supposed that you need to finish everything except the report. You need to finish everything, the main project before the presentation. Then you can make the presentation to the others, right? So there's no any extension on the videos and code. So please submit it before Monday. All right. So that's the deliverables about code and video. And another very important thing is the presentation. So for each of the group, you will have 8 minutes presentation plus 2 minutes question and answers. All right, so 8 minutes. So please limit your presentation within 8 minutes. I know some of the groups you may use more, but the thing is, the audience, they may not have that time, that attention for a very long presentation. And which means it is a skill. It is a skill to limit your presentation within a very short time, and you can still adjust the works and the important parts, and also impress the others. So that's a skill. So in this deliverable, as I mentioned before, I want you to have this kind of like practice to make the presentation of your project or of your work within a very limited time, and also to let you have a feeling about after you presenting the work and how to answer the questions. What kind of like questions you can get from the others, and how you can answer those questions well. All right, so again, next lecture, the same time, we will have our presentation. We will have our presentation. Wait a minute. Okay, so let's talk about that a bit later. Yep. So for the presentation, please limit your presentation within 8 minutes, and then we will have 2 minutes question and answers. Otherwise, we can't finish the presentations within 2 hours. That's the thing. Within 3 hours. That's the thing. That's the thing. All right. So so there is an order about doing the presentation. So I will upload a form. I will upload a form about the peer review. Then we will do the presentation with that order. So the order of the presentation is mainly about the project order. So I didn't make the order of the presentation by groups, but to make it by the projects, because I want the groups which were working on the same project presenting their work one by one. Then you have a better comparison about which group is good and which is not. All right. And again, as I mentioned before, for the presentation, the marks are mainly based on the peer review. So I'm considering not giving any of the marks from me on the presentation, but only by other students. All right, so I will upload a form. I will upload a form of the peer review. Then for each of the students, you need to give the marks to the other groups, not your group, not your own group, but the other groups. And you can mark it from 1 to 10 because the weight is 10%. So 1 to 10. And then I will give an average on all the peer reviews and to make it as the mark of your presentation. All right, and I think the best thing you can get from the presentation is you can have a better feeling about which group doing the project well and which group is not. All right, and you have a better feeling about which project is a good project and which is not. All right, so that's the presentation. Again, I've already. Yeah, that's a good question. That's a good question. So for the presentation, you have 8 minutes to try to organize your presentation something like this. So suppose the other students, they didn't know anything. I mean, they are in the same area, right? So they are the students in this subject, but they didn't know anything about what you did. Suppose it's about that. So what you need to do is you need to first give a very brief introduction about the project you did and your aims. And then during that, the methodology and also the experimental results. And also, if you have videos or left demos, just put it on that. And you can also address some issues or questions that you faced during the project. But I don't suggest you to put put too much on that, because you finished that project already, right? So you solved the problem. So that is practice. This is what I suggest, but it is not limited to that. It is not limited to that. So you can design your own presentation, and the only purpose is that you need to persuade the others that your project is good, is excellent. All right, so that is my suggestion. Sorry, the structure is my suggestion, but you don't have to follow that. I'm quite open to any single format of the presentation. But the thing is, you need to your only objective is to persuade the others. Is to persuade the others that your project is good. And then the others will give you a better mark on this. All right, and what can I say? Yeah. So I suggest everyone make the presentation with slides, not like purely like speak. It's like slides is better. And then I do have some groups. They only have a video, and then during the video they present their work. Something like that. But I do suggest a normal or traditional way of doing this presentation is to use slides. All right. And then during the presentation in the next lecture, I will open the screen sharing function to all of you. And then let's do it one by one. Let's do it one by one with the order that listed in the peer review form. All right, and I got a question on the Azure from Azure that in the report. I think most of you have already write the report for some other projects. So the project report is a very complete report. Then at the beginning, it will be similar as what you have for the proposal, which means you have the abstract, introduction, and the related work. Then in the middle, you will adjust the methodology that you used. You will mention the methodology that you used, and after that, you will have the experiment. And then at last, you will have conclusions and also some appendix if you have, and also the references. All right, so that's the complete structure of that. Why I'm making the report individually, because the group project is 50% weight. Then which means I do need some of the deliverables to be finished individually. Then for the report, you write it individually, but you can write everything you have in the group. All right. So for the group project report, so you write it individually, but you can write everything. It is different from the mid-review report. In the mid-review report, you only write what you did. But in the report, you are supposing to write a complete report. You're supposing to write a complete report of your project by yourself. But I need, if you have 3 members in the group, I want to see 3. I want to see 3 reports. All right, something like this. All right. So if you still have questions on the project, please post your questions in the chat, and then I will answer after the lecture. All right. So, and then let's talk about the final exam. As I mentioned, the final exam is 30% in this semester because of the online teaching. So I moved the weight more on the group project, and to reduce the weight on the final exam, because the final exam is applying online. is applying online, then it is quite different. It's quite difficult to make the final exam a bit fair. Then I'm trying to make it. I'm trying to explain it to you. I'm trying to make it, but I can't make. I can't make a. I can't confirm on that if this like 100% fair to most of the to all of the students. All right. So the final exam is 30%, and then it is a restricted rule that the window of doing the exam is 6 hours. 6 hours. So which means it's an online final exam and making it take home exam, which means it will be similar. It will be similar as what we have. It will be similar as what we have for quiz 2, which means on the time that we start the final exam, then you can download the question paper from the UTS Online, and then you answer the questions and then take pictures or scans and upload them to the UTS Online. All right. So the questions, the actual time that you may need to answer the questions is about 1 to 1.5 hours. It's some kind of like 1 hour or 1 hour and a half. But it is restricted from the university that the window is 6 hours. The exam window is 6 hours, then which means for this subject, the exam is on the it's on the 24th, Wednesday, 24th of June. Then from 12 in the noon, then the window of the exam, which means you can access the question paper and you can upload your questions, will from 12 in the noon to 6 p.m. something like that. But the actual time you may use only about 1 hour to 1 hour and a half, something like that. I do suggest that it is not fair, because if one can answer the questions within one and a half hours, and then a very long window, it is not good for the final exam, because students can cheating on that, right? But that is the rule, so I can't change. Then to make it to make it relatively fair, so I will select after the final exam, after I make the marks, before I release the marks, I will select some of the students to give an interview on the final exam, right, to make sure you're not do something cheating on it. All right, so it is selected. It's not all of you, but it is selected. But I'll definitely do that in case in the 6 hours it is not fair to some of the students. All right, so and that is the format. And for the questions, it is only 30%, and it is probably that most of the students will finish it within 1 hour and a half. And there will be short written answers and long written answers, including calculations. And then in the previous semester, it is restrict open book, but in this semester, it is open book, which means you can get any materials that you can use, and also you can use MATLAB to do some calculation, and also you can use MATLAB to double check with your answer. All right, but to make it fair to the students, I will design the questions. That for most of the students, you're answering similar questions, but the answers will be different. The answers for each of you will be different. I'll try to make it fair to all of the students, but I'll try my best, something like that. All right, and also because it is open book, totally open book, I will definitely make the questions harder than before. I will definitely make the questions harder than before. All right, so any other questions on the final exam? Yeah, post your questions to the chat, and then I can answer. Yeah, that's a good question. There will be around 3 questions, 2 to 3 questions. It depends, 2 to 3 questions, and in each of the questions there will be sub questions, similar to what you have in quiz 2, something like that. 2 to 3 questions and with sub questions in it in each of the questions. All right, but totally is 30%, and you have 6 hours, so you have plenty of time to do it. Yeah, you can make it a Word document or PDF, or if you can't make it, you can handwritten it and take a picture and submit the picture. So it's like similar to what you have for quiz 1 and quiz 2. Yeah. Any other questions? All right. So any questions you can post it to the chat. Then after the lecture, I will answer. And also, if you find anytime if you find some questions to ask, just send me an email. All right. Cool. Then let's go to today's lecture. So in today's lecture, it's mainly about subject review. So in this subject, at the beginning, we gave an introduction about sensors and controls in the mechatronics, especially in robotic systems. Yeah, display. So in the first lecture, we gave some examples. We give some examples about the mechatronic system, which is sensing and control, right? And then I give an activity about this example, which means we use the FACT robot to navigate in the environment and to do the grasping of the object on the table, right? And then in the activity, we ask some questions. So one is, how many problems involved in this application? And the second question is, what sensors and control methods are used in each of the problem? Right? If you remember. Yep. And I'm not waiting it for quite long. Then we conclude those of the questions. The first question is, how many problems involved in these applications, right? So I myself identify 3 problems in it. The first one is about navigation or localization, which means the robot needs to go from an arbitrary starting point to the table, right? So you need to make the robot to have the ability to do the navigation or localize itself in the environment, and then it can navigate it from the starting point to the table. All right, and what sensors we're using? And in this case, as I mentioned, if it's in the 2D NOR environment, and the 2D laser is the perfect one. It's the perfect choice that for you. And also I mentioned before, it's because in the building 11 environment, there are lots of glasses for the wall. Then in this case, the 2D laser may not work on that. Then you may also need RGBD camera as well, right? So that is the first problem. And the second problem is object recognition. So which means if the robot moved in front of the table already, then the next thing is the robot needs to needs to recognize the object on the table, which means it needs to the robot needs to organize there is the object on the table and what's the shape, what's the size, and where it is. Right. So that is object recognition, and we always use RGBD sensors to do that because it's much easier. It is much easier because you can get point cloud, and then you can easily segment the object from the point cloud because the table is flat, right? And then from that segmented point cloud with respect to the object, then you know the location of that, you know the size of that, you know the pose of that, right? And the third problem is the visual serving, as what we introduced in the previous lecture. That's the visual serving. That's the visual serving. Then the robot need to control the arm to pick up the object. Right? And the best way is not doing a look and move, right? So it's doing online control, and the visual serving is the perfect one. And for the visual serving, you can use a single camera, you can use RGBD camera, and also do remember it is grasping. In case you're not breaking, so the gripper will not break the object, and we will use force sensor on that as well. All right. So the in the very first lecture of this subject, we give an introduction with a lot of applications, a lot of examples and applications, and then we do this activity to let you to have a better understanding about the complete mechatronic system or robotic systems. And if you want to do an application similar to what we have for the fetch, then the first thing is you have the idea in your mind that when you organize this kind of project, the first thing is you need to divide it into small problems that you solve. And for each of the problems, you need to think about you use what kind of sensor and what kind of control method to solve each of the problems. Right? This is making you to have a general idea about doing mechatronics or robotics projects. And I do believe you're applying this kind of thinking already to the group projects. All right, so that is the introduction, and then after that we introduced the camera, the single camera. This is the most commonly used sensor, right, in everywhere. It is cheap. It is quite easy to get it and use it, right? And but the most important thing is that if you are using a camera as a sensor in your mechatronic system, you need to know the working principle of the single camera, which means the single view geometry, or we are introducing the projection of the camera. So which means in the 3D environment, you have a 3D point. Then on the image, you have a projection of that 3D point, which is a 2D point on the image. And how can you calculate this kind of projection from a 3D point to a 2D point on the image, right? And we introduce that, and it's quite important. We involve it into some activities, and also we have a sub question of quiz 1 as well. And that is very important. As I said, that is very, very important. All right. So for most of the cameras, they are within a pinhole model. The pinhole model is something like this. The pinhole model is something like that. When we introduce the pinhole model, we introduce the projection model step by step. All right. So if we have a 3D point, and then we want to calculate 2D point, we introduce the central projection and the principal point offset. All right, so this equation, wait a minute. So this equation gives the central projection, then which means when you have a point here and where is the point there, with the origin of the principal point, right? And then for most of the images, because we always use the top left of the image as the origin, then we need to do a principal point offset. And that is the principal point offset. That is the principal point offset. Then, which means if you have a 3D point, very important, if you have a 3D point in the camera coordinate frame, then you can calculate the UV values of the projection by using this central projection with the principal point offset. All right, so that only applies if the 3D point is in the camera coordinate frame. If it's not, it's a general case I've introduced a bit later. All right, so another thing we have, if you remember in quiz 1, is about the focal length. So as we know, the focal length, we only have one lens for the camera, then the focal length should be one number. But after you do the calibration, you will have two numbers, fx and fy. They are nearly the same, but they are different. How we can use that is when you calculate x, then you use fx. When you calculate y, and you use fy. And why there are two numbers, I have explained that already. The focal length now used in this projection, they are with the metric. Wait a minute. They are with the metric of the pixel size. So if f is equal to 800, which means the focal length is 800 pixels, and the pixels for each of the pixels, the size on the x and y, they are not exactly the same. So that's why the fx and fy, they are slightly different. All right. So this is also, again, the central projection with the principal point offset, but it is in a homogeneous matrix format, And when you want to calculate this, you need to formulate this 3x4 matrix with focal length. Here is fx, here is fy, and the principal point, and the 0, 0, 0 here. And if you have a 3D point x, y, and z, simply add 1 to make it homogeneous, to make it as a homogeneous 3D point, then you can use this function to calculate a 2D homogeneous point, the 2D homogeneous point of the projection on image. And how can you convert that 2D homogeneous point, which is a 3x1 vector, to a UV? Then which means you use the first element divided by third one, and that is your U. You use the second element divided by the third one, that is UV. All right. So that is the matrix format for the central projection with the principal point offset. And also we can rewrite this equation into here. This is homogeneous one. And again, this central projection with the principal point offset can only apply if your 3D point is in the camera coordinate frame. And in this case, if you rewrite it like that, we have a matrix K. And matrix K is a 3x3 matrix, only include the camera calibration information or parameters. Then this K matrix, we called it camera calibration matrix or camera intrinsic matrix. All right. And then we introduced the camera projection, but with general case. A general case means if you have a 3D point, but that 3D point is not in the camera coordinate frame, but in the global coordinate frame. For example, if you have a camera on your robot, and then when the robot moves, then you can't get a point in the camera coordinate frame, but you have points in the global coordinate frame, right? So in this case, how can you calculate the projections? And it is quite simple. So suppose you have a 3D point in the world coordinate frame or global coordinate frame, and also you have a camera pose in the global coordinate frame, then which means you can use this camera pose to first transform that 3D point from the global coordinate frame to the camera coordinate frame by using the camera pose RNT. Then after that, you can use central projection with the principal point offset, right? So after you have a 3D point in the camera coordinate frame, then you can use central projection with the principal point offset. And how to do that is you have a rotation and translation, which means you have a pose of the camera, and then you can use that pose to transform that 3D point from global coordinate frame or world coordinate frame to the camera coordinate frame. And here is the general formulation. Again, if you remember, so this formulation is the homogeneous matrix formulation of the central projection with the principal point offset. And here it is XCAM, right? So we change the XCAM, be replacing the XCAM by this. The X is the 3D point in the global coordinate frame, and also again it is a 4x1. It is 4x1 because it's homogeneous. You just add 1 at the last element, which is X, Y, Z, and 1. All right, and this is the transformation matrix. R is a 3x3 rotation matrix, and C is a 3x1 translation of the camera or the camera center. All right, so R is the rotation of the camera pose, and C is the translation or the camera center of the camera pose. And don't forget, it is a minus there, right? And this is a 4x4 matrix. Then together, this 4x4 matrix with the capital X, it calculates the X cap. Then we can rewrite it to a general formulation. It is something like that. And as I mentioned before, this is a 3x4 matrix. 3x4 matrix. All right. And do remember, this is a 4x1 matrix and the 4x1 vector, and the small x is 3x1. That is a homogeneous 2D point. And how to convert it into the normal 2D point U and V, which means U is equal to the first element of the X divided by the last one. And the V is the second element of X divided by the last one. And then you have U and V. So this is the general case. So if you have a question in your future that to say there is a point in the global coordinate frame, X, Y, Z, and then it gives you the camera pose, R and T, or R and C. T is the same as C. Then it's asking you to do the projection from the 3D point to the 2D image. Then you can use this general formulation of the camera projection to do that. Right? You just put the 3D point there with the homogeneous one, adding 1 at last. And this is the camera translation, T or C. This is the camera rotation. And that is the camera calibration matrix. And that's it. You can calculate it. All right, so that is for single camera, the camera projection, or we call it single view geometry. That is quite important because if you want to use some information on the image, you need to know where is it from. From the you need to know how it gets from a 3D point, which means from this single view geometry, or we call it camera projection, you know the relationship between a 3D point in the environment and also the 2D corresponding 2D projection on the image. All right, so that is for the camera geometry. And here is a summary about the projection chain. And again, this is similar. Suppose you have a point in a world or global coordinate frame, then you need to first transform it into the camera coordinate frame, and then do the projection and convert it into the pixel grid. And if you don't want to remember those things, then just remember this equation. This is the general case. You just put the numbers on it, you calculate it, then it's done. All right. So that's the camera geometry. And then we have an activity on that. So do make sure you know how to do this activity about the projection. All right. So practice on yourself after the lecture, and do make sure you know how to do this activity by yourself. And also, if you remember, we have the questions on the in the quiz one as well about this projection. So do make sure you know how to do this projection. Not only on the central projection with principal point of that case. So which means not only a 3D point in a camera coordinate frame, but also if you have a 3D point in a global coordinate frame with the known camera pose, then how to calculate the projection. Right. So make sure you know how to do it. And after we introduce the camera geometry, then we introduce the calibration, because you need to use the camera calibration parameters or intrinsic parameters, which are mainly the focal length and principal point, into the projection. And for each of the camera, if you have a fixed length camera, then the intrinsic parameters will not change. Which means if when you buy a camera and want to use it in the in your project, then if we can do a calibration to calculate the intrinsic parameters, then you can use it later to do some projections or something. Right. So that is why we are doing camera calibration. And what we can do is we can use the calibration toolbox. And with the calibration checkboard, and the checkboard is quite easy to detect the corners. Then they use the corners and also an optimization to optimize the camera intrinsic parameters. All right. So I think all of you have worked on that already, and also we have quiz one on that as well. All right. So for more details, if you want to find out what's the things behind, so follow the link on it and you will find more information on that. All right, so the calibration is, if you buy a camera that is fixed length, you want to calculate the intrinsic parameters, then you want to use it in the further control or calculation, then you use camera calibration. And after the camera calibration, you can get the focal length. Again, there are two numbers of focal lengths, and I've explained it why already, and also the principal point, and also some distortion parameters. But you don't have to worry about it at the beginning, but you definitely use it later if you want. All right. So that is the camera calibration, and then after that we introduced a very simple but very commonly used image processing technique. We call it convolution. Convolution is some kind of like you modify the image, you modify the pixels by a function, by a linear function, and also by a local neighbors of other pixels. And here the linear function, we call it the kernel. The kernel is also a matrix. So if you suppose the image is the matrix, the kernel is also the matrix as well. And then the convolution, if we apply this kernel on this image, it is like for the corresponding elements, you time them together, and after that you sum them together. So which means 10 times 0 plus 5 times 0 plus 3 times 0 plus 4 times 0 plus 5 times 0.5 plus 1 times 0 plus 1 times 0 plus 1 times 1 plus 7 times 0.5, something like this. And you sum them together, you will get the value of the pixel in the middle of this image. All right, so that is the convolution. And we also have this activity. So for most of the cases, your kernel matrix is a small matrix. It can be 3 by 3, 4 by 4, 5 by 5, but relatively small. But for your image, it is larger. It is larger. Normally is 640, 480 or something bigger. All right, so here I'll give example to make a larger image on a smaller kernel matrix. And what you need to do is you first calculate this convolution with a subset of the image which has the same size of your kernel matrix, right? And after that, you calculate the value here. And after that, you move it, you shift it to the right, you calculate another part of the image, which you still have the same size to the kernel matrix, and then you get that kind of value, and you put the value there. And you shift it down. You also have a 3 by 3 matrix on the image, and you apply the kernel matrix. Then you have the value here. And you shift it to the left, then you have this submatrix, and you calculate the value and put it here, something like that. All right. So that is the convolution with the values. With the image, which is larger than the kernel matrix. And also this applying different kernel metrics, you will have different pre-processed image that you can use. For example, blurring, you can use Gaussian kernel, and you can use the edge kernel to detect the edge from the image as well. And this one is this is a typical like edge kernel which can enhance the edge, which you can see here. So that's the edge, right? That's the edge. So there are some other kernel metrics, and also you can design your own kernel metrics, which you can apply to the image to do some processing, pre-processing on the image, right? So that is the convolution. And after that, we introduce the RGBD camera and also the stereo. So we introduce stereo first, but I switch it a little bit later to later lectures. But for the stereo and RGBD cameras, there is one same thing for both of the two sensors, which means from stereo and RGBD cameras, you can get the depths. You can directly get the depths. This is comparing to a single camera, because in a single camera, as I mentioned before, so you can't directly get the depths. So every single point along this ray will project the same point on the image. So which means you don't have the ability, so the camera cannot have the ability to calculate the depth, so to recover the depth. So that's why we are using stereo or RGBD camera. And for stereo camera, why we can calculate depth is because we have another view. From the right camera, we can still have the projection on the point, and then we know the same point will be along this ray as well. And then the intersection of the ray will be the location of the 3D point. And this method, we called it triangulation. And this method, we called it the triangulation. All right, so how to do the triangulation? So you've already got it in the quiz. So how to calculate triangulation is you first calculate what is XL and XR. And again, the XL, XR, they are with the origin of the principal point. So which means if you have the UV value of the feature on the left and right image, then the first thing is you need to minus the principal point to get the XL, XR, YL, and YR. All right, and after you get XL and XR, use this equation to calculate Z. Because in this case, you know what is XL, you know what is XR, and you know what is B. B is the baseline. So between two camera centers. I explained it before in the quiz too. And also the focal length. Right, you have everything here. You can calculate Z. You can calculate Z. Right? And after you calculate Z, you can put the put Z here, you can calculate X. Right? And this is the XZ is considering the XZ plan. If you want to calculate Y, you just replace Y here, the capital Y here, and the small YL here. And then you can calculate Y. You can calculate Y. All right, so always calculate Z first. Z is some kind of like depth, but it's not a true depth of some kind of depth you want to first calculate. And after you calculate Z, using that equation, you can calculate X and Y. That is the triangulation. And again, this triangulation, you can get a 3D point. You can get a 3D point, but this 3D point is in the left camera coordinate frame. That 3D point is in the left camera coordinate frame. Again, this 3D point is in the left camera coordinate frame. All right, so do making sure. So if I'm asking you to calculate the 3D point in the right camera coordinate frame, you need to do a transformation from left to right, something like that. All right, so that is the triangulation, and we have one activity on the triangulation in the lecture, and also we have one question in the quiz too on triangulation. So triangulation is quite important when you use a 3D. When you use a stereo camera, so the most important thing for using 3D camera is stereo camera is you can calculate the depths. You can calculate the depths directly from a stereo camera. All right, so that is stereo. Then we introduce the RGBD camera. So we first introduced the principle. So the principle of the RGBD camera, most of the RGBD camera, especially the Kinect camera, it is the structured light. But I should say for the newest RGBD cameras, they are using time of flight at the moment. The newest, but most of the cameras, they're still using structured light. So what is structured light? What's the principle behind Kinect? Is there is a projector, and it will project a design pattern, IR pattern. And then there is an IR camera. It can capture the IR pattern, and the pattern on different objects, the pattern will deform in different shapes. Then they will compare and do some calculation based on the change on the pattern, and they can calculate the depth of each of the pixel. And then there's a normal RGB camera, and they do a calibration between them. Then they can relate each of the pixel with the depth from the structured light. So that is the principle. And we also introduced for the RGBD cameras, what we commonly use to manage or to use the data is the point cloud. Because for each of the pixel, it has a depth. then it can be easily convert that pixel into 3D point in the camera corner frame. But I mean to the 3D point, and also because each of the 3D point has an RGB, has a color from the RGB image, then you can present the scene by using the dense point cloud, and with each of the point has a color, as will be showed in the figure. So that is point cloud. And also we can calculate some other properties or characters for the point in the point cloud. For example, the norm, the normals of the surface or something, right? So that is the point cloud we always use in the RGBD camera. And for the RGBD cameras, we also introduced the different cameras that which you can use with different like properties of each of the sensors. For example, if you want to have a larger resolution of the depth image, you can choose Connect 2. Or if you want to use it in a longer distance, then you may use Connect 1. But when you want to apply a RGBD sensor into a relatively closer distance, but with higher accuracy of the depth, you may use the real size, something like that. So there are multiple RGB cameras that you can choose. Then you need to make sure that fits your project, fits your application environment, something like that. All right. Then after that, we introduce the time-of-flight sensors. So we first introduced sonar, then we introduced the ultrasound, then LiDAR, then a laser measurement system. So it's like LiDAR, it's like similar. Then we didn't introduce radar, but it will be similar. So all of the sensors, they are time-of-flight sensors. The time-of-flight sensors, and we also introduced a method which can extract the lines from a 2D laser scan or 2D LiDAR. All right, so that's the time-of-flight sensors. And also, as I mentioned, if you have projects which it is in the outdoor environment, for example, the autonomous driving, then it is better to use 3D LiDAR. Use 3D LiDAR because 2D they contains limited information. They don't have information on the vertical direction, so it's better to use a 3D LiDAR, and a Violet Eye or RobSense, they are the choices that you can use. And also for most of the team or projects they are doing autonomous driving, they definitely use 3D LiDAR. And for 3D LiDARs, they have different models. For example, they will have like 16 lines on the vertical direction, which means 16 lines on the vertical direction, or they have like 32 or 64 lines on the vertical direction. But the price are different as well. All right, so and also if you have a project in the indoor environment, which means the environment for example, the robots moving in an indoor environment, which means the environment is flat. The environment is flat. And in this case, a 2D LiDAR is always the best choice, because if you use 3D LiDAR, the computational cost is a lot. And in 2D environment, sometimes you don't have to use that. So in the 2D environment, the 2D LiDAR or 2D laser is the proper choice for your project. All right, so that's the time-of-flight sensors. And after we introduce those sensors that we commonly use in the Mektronix systems, we introduced a feature extraction and checking, which means if you want to use some information from the image, you may not use the complete image. You can just use some of the information, which contains some of the parts of the image, which contains more or most of the image, most of the information from the image. Then you can use them to your control. You can use it in your control algorithm. And those parts, we call it features. We call it features. And then we introduced two typical features. One is edge, the other is corner. and corner is much more used in the real case because it's quite easy to extract and quite easy to match, and also it contains somehow contains more information, but not more structural information compared to edge. But it's quite easy to use. And in the feature extraction and checking, we introduced three methods. One is high-risk corner detection, and second is SIFT, and third is SURF. We introduced three feature extraction methods. And SIFT features are quite commonly used because it can provide you a sub-pixel accuracy feature extraction, and also it provides the descriptors. Then you can do the correspondence, you can do the matching, So imagine that when we do the triangulation, so we need to check the feature from different images, and then we can do the triangulation. And also, if you remember when we introduced the Building Roma in a Day project in the video, so if you want to 3D reconstruct the virtually 3D reconstruct the environment by using the point cloud, then you need to check the same feature in different images. All right, so this is why we introduced the feature extraction and checking. So for most of the time, you may need to check the features extract the features and check the features from the camera, from the images during your control. And that is why we're introducing that. And SIFT is quite good because SIFT has sub-pixels accuracy of the feature extraction, and also it has descriptors which you can easily to do the matching of the features between different images. All right. So for the features, the SIFT features detect the maximum and the minimum of difference of Gaussian in scale space. So you first make the Gaussian parameter of the image, and then extract the maximum and minimum of difference of Gaussian in the scale space, and make the features make them as the features detected. So that's the feature detection. And another part of the SIFT is called descriptor. Descriptor means is a description of each of the feature. And in the descriptor, it is 128 dimensions, which means 128 values in the vector. That is the descriptor. And how to calculate, I've introduced about how to calculate that. It computes the magnitude and orientation of the gradient, and also make the gradient into histogram with respect to the directions. And then if you do not remember how we can calculate those descriptors, go back to the slides in the lecture. All right. So for SIFT feature, there are mainly two parts. One is the SIFT feature detection, and the other part is the SIFT descriptor. All right. And I've introduced how to calculate the feature locations, and how to calculate the descriptors already. All right, and for the descriptors, do remember it is 128 dimensions of each descriptor, and we can use the descriptor to do the matching. If you remember, I gave an example, I gave a run on the SIFT code, then I think you've run it by yourself already, and we can do the matching. All right, so that is SIFT. Then we introduce SURF. SURF is called Speeded Up Robust Features. And it is speeded up in both the feature locations and the descriptors. All right, so let's see how it make it speeded up. All right, so the SIFT, for the feature locations, for SIFT, it approximates the Laplace of Gaussian with the difference of Gaussian. And in the SURF, it approximates the Laplace of Gaussian by using a box filter. It is a further approximation, but it's quite fast to calculate because if it's a box filter, it is super fast applying to the image. All right, so that is speeded up on the feature detection point of view. Then on the descriptor, if you remember, for SIFT descriptors, there are 128 values. But for SURF, it is 64, which is half comparing to SIFT. And how they reduce it from 128 to 64 dimension. Then if you don't remember about that, go back to the lecture notes in the feature extraction checking and double check. You know how it's done for reducing the dimensions of the descriptor. All right, so that is SURF. So SURF reduce the speed on both the feature detection and the descriptor. All right, and for the feature detection, it approximates the Laplace of Gaussian by using a box filter. And for the descriptors, it reduced the size of the descriptor from 128 to 64. All right, so that is SURF. And also we introduced Harris corner detection. The Harris corner detection is a very old one. It's a very, very old one, as I mentioned before. And they use the second order moment metrics to detect the corners, and they really detect the corners. I apply it as I mentioned to you. I apply it the first year of my PhD, then to some photogrammetric images, which means got images from the UAV in the sky. Then we got some images to the buildings behind, and then the Harris corner really detect the corners of the buildings and roads. All right, so that's the Harris corner detection. The Harris corner detection is there's an issue that it's only detecting the corners. There's no matching. There's no matching on that. That's the issue. There's no matching on that. So in this case, it's only detecting the corners, and also it is not sub-pixel accuracy, if I remember correctly. All right, so that is Harris corner detection. And after we introduce the feature extraction and checking methods, another thing is there are some outliers for the checking. So if you apply SIFT or SURF to detect the features from the two images, and you applying the feature matching by using the descriptors, then there will be a lot of wrong match. We call it outliers. How to remove the outliers? Right. So we introduced the RANSAC. RANSAC is a very, very famous method, and also it works quite well. If you remember, so I didn't explain the algorithm like that, but I explained it with an example about the line fitting. Then, because the most important thing we want to apply the RANSAC is about reducing the outliers of the matching of the features between two images or multiple images. And what we can do is we apply the epipolar constraint, which means suppose we have a point on the left and we have another point on the right image. Then here we can calculate a fundamental matrix, which is a 3x3 matrix. Then we can and if they are correct match, if they are corresponding to the same 3D point, which is their correct match, then this equation is equal to 0. So we use that as the constraint, epipolar constraint in the RANSAC, in the RANSAC. And how to do the RANSAC? To remove the outliers. So the first thing is you randomly in your first run, suppose in one of the run, you randomly select 8 points, 8 correspondences, 8-point match. So 8 correspondences. And from the 8 correspondences, you can calculate the fundamental matrix F. And after you have the F from 8 randomly selected correspondences, you can test all the other correspondences. Right, so you have F already, so you apply this equation to all the other correspondences and to see what's the number here. And it's supposed to be 0, right? But it's not perfectly to be 0. Then you give a threshold to say my threshold is 0.2. Right, so any correspondences, if this equation is smaller than 0.2, I count it as a number. All right, so for this run, I will count how many correspondences they are within my threshold. And that's your one run. And then you did another run. So for another run, for the next run, you still randomly select 8 points to calculate another F. And use that F to apply, and use that F to apply it to all the other correspondences, and to check how many correspondences are within your threshold. And you do multiple runs. Suppose you do thousands of these runs, right? So you find one run that with the maximum number that correspondences within your threshold. And in that run, those numbers are your correspondences. All right, so that is the process about using RunSec to remove outliers of the feature matching, And I do have this as homework or activity, I can't really remember, but do make sure you know how to do the RunSec for the outlier removal. All right, especially for the outlier removal of the matches of the features, of the feature checking. All right, so try to write it step by step to explain about this RunSec for the outlier removal of the feature checking. All right, so that is RunSec. That is mainly what we have for the feature extraction and checking, right? So we introduced what are the features and why they're using features, and after that we introduced some popular feature extraction and matching methods, safe and serve and Harris corner. But safe and serve, they have matching already. They have matching methods already because they have correspondence, they have descriptors. And because when we do the feature matching by using the descriptors, there are some outliers. And how can we remove those outliers is we use RunSec, and also we applied epipolar constraint. All right, so that is for the feature extraction and checking. So the feature extraction and checking finished the sensor part. So we have sensor part to introduce the, so we have one lecture about introduction, and we have lectures to introduce camera and stereo camera and RGB sensors and time-of-flight sensors. And after the sensor lectures, we introduce the feature extraction and checking. And after that, we have 3 lectures about the control part. The 3 lectures are mainly about the linear continuous time system, control system, and the linear discrete time system and nonlinear discrete time systems. All right, so we first introduced the linear continuous time system because it's the most easiest one. And that's the standard formulation of the linear continuous time system is something like this, which is x dot is a function is ax plus bu. So x dot means the derivative of x with respect to time is a linear function of x and u. X is the state and u is the control. And output y is equal to cx plus du. This is standard formulation for the linear continuous time system. And if you remember, we introduced a lot of examples that you can formulate the control system from a real case, right? So So why we're using state space model for the control is it's quite easy to formulate from the root case. If you remember, we always start from this Newton's second law, to formulate the physical formulation, and then we can convert that physical formulation into this standard formulation of the state space model. Right, so this is the general formulation of state space model, and we introduce the solution of the model of the system. The solution of the system means if you know what is the initial state, then you can calculate the state at any time by using that equation, right? So that is the equation of the solution. Just remember it, or just let yourself know how to find it if there's a question on that. But the thing is, the solutions for the linear continuous time system and the linear discrete time system, they are different. They are different. Do you remember they are different? So choose the correct equation for the solution. All right. So that is the linear continuous time system, the general formulation and its solution. And after that, we introduce the stability. So what is called a system is stable is so if a system is stable, which means from any initial state, the state will converge to zero as the time increase. That is stable. And we want our system to be stable, right? And it's easy to control. But how can we check the stability? How can we check the stability of the system? The first thing is the stability only depends on the matrix A. So they are A, B, C, and D matrices, right? And the stability only depends on the matrix A. Only depends on the matrix A. And the condition of the stability is that if all the eigenvalues of A are negative or have negative real parts, then which means that is stable. And we introduced about how to calculate the eigenvalues, right? So if you calculate the eigenvalues by hand, you can use this equation. And when you have similar questions in your final exam, for example, so calculate it by that, and also please double check if the eigenvalues you calculated are correct or not by using MATLAB functions. But don't directly apply the MATLAB functions for that. All right, so I need to know your calculation process. All right, so that is the eigenvalues, how to calculate the eigenvalues. And after you calculate the eigenvalues, you need to apply the criteria about the stability to check if they're stable or not, right? And the criteria or the conditions of the stability for the linear continuous time system is that all the eigenvalues are negative or have negative real parts. Then the system is stable. All right, then which means suppose you have two eigenvalues, which is -1 and -2, then that is stable, right? So suppose you have two eigenvalues, which is 1 and -1, then which means it is not stable because one of the eigenvalue is not negative. Then which means if you have only one eigenvalue is not negative in the linear continuous time time system, then it is not stable. All right, and again, do remember the criteria or the conditions for the stability for the discrete time system, it is different comparing to the continuous time system. Do remember about that. And then we introduce the controllability. Why we're introducing that is, if you remember, so if it's not controllable, if it's not stable, we can do a state feedback control and we apply the pole placement, or we can choose the optimal K by using the optimal control, make it stable. But the thing is, not all the system can be can change the stability like that. So not all the systems you can change the stability by using the state feedback control. Then how to check that is the controllability. So before you're applying the pole placement or optimal control, then you need to check the controllability if the system is controllable or not. And how to check that is, suppose you have this system, continuous system, you calculate the controllability metrics, and not always if your A and B are with the dimension of 2, you just calculate the first 2 is fine, or first 3 they're fine as well. Then if this controllability matrix is 4 rank, then it is controllable. Otherwise it is not. And how to check it is 4 rank, there are 2 methods I've introduced. I've mentioned it already in the quiz 2. Then one is the intuitive way. If you can find the row can be presented by the other row linearly, then that is not 4 rank, which means it is not controllable. And another way is the mathematical way. You can calculate the determinant of that matrix. If the determinant of that matrix is equal to 0, then which means it is not 4 rank. All right. So for checking the controllability, the first thing is you need to calculate the controllability matrix correctly, and then after that you check the if it's 4 rank or not. If it's 4 rank, then that is controllable. If it's not 4 rank, that is not controllable. All right, so that's the controllability of the linear continuous time system. Then we introduce the linear discrete time system. And this system is different from the continuous time system if you can compare. First, there's no dot anymore. Right, so this is the discrete one. There's no dot anymore because it is discrete. It is discrete. The discrete means that the time is not continuous. It's time step. It's time steps, k, instead of t. So which means you can't calculate the derivative of the state with respect to time. So that's why there's no dots there. But instead, the system or the formulation is xk plus 1 is equal to ax plus du, which means that the state in the next step is a linear function of the state and the control in the current step. Right, so that is the standard formulation of the linear discrete time system. So if you have question to giving you a control system and to let you to answer some questions, the first thing is you need to identify if there's discrete time system or a continuous time system, and then you can choose the right conditions and the right equations to answer the question, right? And as we introduced before, that the discrete time system, it can be naturally discrete. The state can be naturally discrete, or it can be converted from the continuous time system. And if we want to convert it from a continuous time system to the discrete time system, it is an approximation because you make that time step. And we suppose the values of the state within each time interval, they're constant, something like that. All right, so for the linear discrete time system, we still have the solution. So the meaning of solution is the same comparing to the linear discrete time, linear continuous time system, but the solution is different. The equation is different. So that's why I mentioned the first thing you need to identify if the system is continuous or discrete. It's continuous or discrete, then you can use different equations for the solutions. All right. And we have this question in quiz 2 as well. And we give a lot of examples about how to formulate the linear discrete time system from a real application to the control system, right? And this is one of the example as the activity about supply chain. I think this is a very good example. So we have some other examples. So do make sure you can formulate the control system from the examples by yourself. All right, and here, so we have three variables in the state, and then we can have different equations together. Then we can also formulate as a matrix format as well. All right, so I do suggest if you have a question about formulating the real case as a linear discrete time system, it always helps to draw this kind of figure, and that will definitely help you to formulate the the control system from the real case. And also do remember, if you want to formulate the real case, the real problem into the linear discrete time system, always find what is xk plus 1. Always find what is xk plus 1. If your xk plus 1 is a linear function, if you find a linear function of xk and uk to calculate xk plus 1, then you solve the problem, right? So that is the formulation of the linear discrete time system. And do make sure for all the examples I have in the lecture notes, and make sure you know how to formulate it from the real case. All right, so that is the formulation. And after that, as I mentioned before, so the linear discrete time system, it can be naturally discrete, or it can be converted from the continuous one to the discrete one. And this converting, or this transformation, we call it discretization. So suppose you have a linear continuous time system, and look at there, there's a dot. All right, then how to convert it into discrete time system? And we introduced two methods. The first method, we call it the Euler method. The Euler method, it starts from the definition of the derivative. The definition of the derivative. So the derivative of the x, which is x dot, is equal to limit ts towards 0, then the difference between k plus 1 ts minus k ts divided by the ts. But because we can't do the limit, so if we delay the limit, that is approximation. So which means the x dot is approximately equal to xk plus 1 minus xk divided by ts. Ts is the time interval, right? And after you have that, you can replace x dot by using this. Then which means you only have xk, you only have x and u and xk plus 1. Then you can change the continuous time system to the discrete time system like this by using the Euler's method. All right, so that is one of the methods which you can use for discretization. And the other method we call the Tustin's method. The Tustin's method starts from the trapezoidal rule, so which means xk plus 1 minus xk is the integration of x dot from k to k plus 1, right? And because x dot is equal to ax plus bu, then we can replace that. We still do this integration, but with the trapezoidal rule, then we can make it approximately equal to this one. And after you have this equal to that, you can make an xk plus 1 equal to xk case, equal to ax plus bu case. Then you use the Tustin's method to do this discretization. But as we can see, for the discretization we've done from the same continuous problem, but by using different methods, the results are different. Right? So this is the Euler's method. This is the Tusney's method. They are different. But why they're different? Because, as I mentioned, the discretization, which means you transform the linear continuous time system into discrete time system, it is an approximation. Right? So the two methods are doing two different approximations. That's why the results are different. All right, so that is discretization. And stability. And stability. The stability, the meaning of the stability is exactly the same. If the state will converge to zero when the time increases, then it's stable, right? But how to track the stability is slightly different. The same thing is for the discrete time system, the controllability also only depends on the matrix A. Only depends on the matrix A. And also we need to calculate all the eigenvalues of A. And the method about how to calculate eigenvalues is exactly the same. But the conditions or the criteria are different. For the continuous time system, the criteria, the conditions of the stability is that if all the eigenvalues are negative or have negative real parts, then that is stable, right? And in here, for the linear discrete time system, if all the eigenvalues are between -1 and 1, that is stable. Otherwise, this is not. Right, so which means the stability, the criteria or the conditions of the stability for the discrete time system is different. It's different. So do remember when you have this kind of question, you have to first calculate the eigenvalues, and correctly, and then you need to answer the conditions or criteria about the stability and make the conclusion if it's stable or not, something like that. And the criteria or the conditions for the discrete time system is different. It's between -1 and 1. It's not minus. It's not minus or negative. All right, so that's the stability. And we have some examples about the stability, if you remember. So so try to make sure you know how to calculate eigenvalues. And also, I do suggest you double check with the answers with MATLAB to make sure that's correct. All right, and don't write a solution like that. You don't have to copy it in because in most of the cases you can't do that. All right, so and then we also introduced the controllability, right? So if you find your linear discrete time system, it is not stable, and you want to use state feedback control to make it stable, then the first thing is you need to identify the controllability. And again, the controllability matrix is exactly the same, and the criteria is exactly the same as well, comparing to the linear continuous time system. So for the controllability, it's exactly the same comparing to the continuous one. But for the stability, they're different. All right, they're different. And then we have some activities about how to check the controllability. And do remember, practice on those, and to make sure that you know how to check the controllability. So you know how to calculate the controllability metrics correctly and how to check the full rank or not. Right. All right. So practice on the activities and make sure you know how to do it. All right. And we also introduced ultimate control. So we introduced ultimate control for both the continuous time system and discrete time system. Right. And for the ultimate control, it's the same. Suppose we have a linear discrete time system and we find that it's not stable. Then we use the state feedback control, so which means we replace the UK by minus kx. And then you have a new system that is xk plus 1 is equal to a minus bk x. And you knew a, which is equal to a minus bk. A minus bk already, right? And if we make this new a stable, then it is stable, right? We can use pole placement to choose to choose some values of the k that to make the new a have all the eigenvalues between -1 and 1, right? But you have multiple choices of k. How to get the best one, which is we introduce the optimal control. And in the optimal control, we want to find a k, which is the optimal one, such that the performance index of this is minimized. And again, the performance index and some equations in the discrete time, in the optimal control in the discrete time system is a bit different from the continuous time system. So do make sure that you use the correct one, right? So the optimal control wants to find the optimal k that to make the performance index minimized. That is the objective of the optimal control. And then how to solve it is we can solve a P matrix from the Riccati equation. So from the Riccati equation, we can solve the P. And from getting the P, we can calculate the K. And from K, we can calculate the U. Right, so that is the how to solve the optimal control. All right. So in the last lecture of the control part, we introduced a nonlinear discrete time system. So which means the system is still discrete, but it is nonlinear. Then how can we find it's nonlinear? Because it is here. So it is still a function between the xk plus 1 and xk. But the function is not linear anymore. It is not linear. It is f. It is f. So for the linear case, it's xk plus 1 is equal to ax plus bu. But here, the xk plus 1 is equal to f, which is a function of xk and uk. So that is the nonlinear case. And in the nonlinear case, because it is so complicated to analyze the properties of the control system. So we introduced the equilibrium. The equilibrium point. The equilibrium point is that. So at that point, the state will not change forever. That is the equilibrium. That is equilibrium. So which means at the equilibrium point, that is for the equilibrium point, your state will constantly equal to the number of equilibrium. So which means at the equilibrium point, the state will not change. That's the equilibrium point. All right. So we make from the definition, we can calculate the equilibrium points of the system. And how we can do that is, suppose we have a nonlinear equation, and because we know for the equilibrium point, the state will not change, then which means the xk plus 1 minus xk will be equal to 0 because the state will never change, right? We apply it into this equation to get xk plus 1 minus xk is equal to this equation minus xk, that will be equal to 0. And you get the solution from that equation, and that will be your equilibrium point. And the equilibrium points will be multiple. And sometimes it may be not only one. All right, so those are the equilibrium points. So suppose you have a question, and with a nonlinear discrete system, and if it's asking you to calculate the equilibrium, you simply apply xk plus 1 minus xk equal to 0, combining the equation with the function, with the control system function together, then you can have an equation, which means something equal to 0, and you solve that equation, and the solutions are the equilibrium points. All right, so I have some other activities. So do make sure you know how to do that. All right, so make sure how to do that by yourself. All right, so after that, we introduce the linearization. So if you have a nonlinear discrete time system, we can linearize it. We can linearize it at the equivalent point. We can do the linearization to make it as a linear discrete time system. But this is linearization is approximation as well, right? Because it is nonlinear. So we apply the first order Taylor expansion, then we can make the linearization. And because we linearize the system, then we can check the stability on the linearized system, right? Then we can check the stability on the equivalent point. And here we introduce the Y for equivalent point because equivalent point never changed. The state never changed. But why we are checking the stability? I give an example about the inverse pendulum, right? So inverse pendulum, if at this state, it is stable. So it is an equivalent point because the state will never change, right? But if you put a little bit change on the state, it will directly change. So that is not stable. So which means at that equivalent point, it is not stable, right? And if it's not stable, we can still use the state feedback control to make it stable on the linearized point. But the thing is, all about this, all the linearization, all the stability, all the feedback control, they are at the equivalent point. We can't do that at any single point on the nonlinear discrete time system because the nonlinear system is so complicated. All right, so it is so complicated. So which means we can do the linearization, stability, and state feedback control only on the equivalent points, only at the equivalent points, one of the equivalent points. All right, so those are the linear discrete time system. And after that, after we finish all the control parts, then we introduced an integration of the sensors and control, and that is the visual serving. That is the visual serving, and we introduced a very traditional method about the classical traditional method about visual serving, and we apply it as an example on the end effector mounted. So, for example, you have a camera mounted on the camera hand, and how to do this control, right? How to do this control, the visual serving. So the aim of this visual serving is to minimize the error between the desired feature location to the current feature location. So, for example, in this case, the blue one are the desired location of that object, and the blue ones are the current location, right? So we want to change the camera to make the object align with the blue one, which are the desired one. And also another example is about the 4-point one. That is quite much easier to understand, right? And we want to minimize that. So this is the error, and S star is the desired feature location, and S is the current calculated location, and the E is the error between them. It's the error between them, right? And if S star is selected, and if we choose the controller as the velocity controller, which is a sixth of 3D velocity, the first three are the linear velocity, and the second three are the angular velocity, right? And if we calculate the derivative of the S or the E as well with respect to time, then that is equal to LS times VC. Then the LS is called the feature Jacobian, right? Feature Jacobian. Then, which means, and here is also equal to E dot. Is equal to E dot. All right. So Y is equal to E. The E dot is also equal to the feature Jacobian times VC, as I mentioned before. S star is constant. S star is constant. All right. So which means in this case, if we know what is E dot, and if we know what is the feature Jacobian, then we can calculate the VC, which is this is what we want for the video serving. So we want to get the control, which is velocity of the camera, right? But for the E dot, let's see how we can get E dot and LE, right? So for the E dot, if we don't want to directly reduce all the error, all the current error, because it contains error as well, right? So if we don't want to reduce the current error, we want to reduce a percentage of the current error. So which means if we suppose to select lambda equal to 0.1 or 0.2, we want to reduce 10% or 20% of the error, then we can make the E dot approximately equal to minus lambda times E. So minus 0.1 times E. So we have, if we can calculate E, then we can calculate E dot, and then we can put it there, right? And after you, suppose you can calculate the error, E, then in this case, we can calculate the velocity of the camera by minus lambda times the pseudo inverse of the L and times E. Suppose we know E, we know lambda already. The pseudo inverse can be calculated from the L. So if we know L, then we can calculate the pseudo inverse of L. When we put it there, then we can calculate the VC, right? So from now, if we know what is E, and if we know what is L, then we can get the camera velocity, right? So suppose we know what is E, then we just put E here. We know what is L, we put L here to get the pseudo inverse of L. Then we put the pseudo inverse of L there. Then we can calculate VC from this equation, because lambda, you know it already, right? Then the following, I'm showing you how to get E and L. So as we know, if we have example that we have 4 points, and we considering 1 point now. We're considering 1 point now. So if we want to calculate the 2D point X and Y, it can be calculated from the U minus the principal point on the U direction divided by F. So that is the small x with the real scale, not the pixels. And then from Y we can do a V minus CV, which is the CV is the principal point on the Y direction, a Y coordinate or V coordinate divided by F as well, right? So we can use this equation. Suppose the red dot, this red dot is the desired UV values that for one of the feature, for one of the dots. Then we can use this equation by replacing the UV values of by using this UV values, the UV values of this point. Then we can calculate the XY for the S star, All right. So we can simply calculate the other 4 by using this as well, and then put them together, XY, 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 put them together as a column vector, and then that is your S star. All right. And the next step is calculate this S. Suppose we know the UV value of this real point, which is corresponding to that. And then we put the UV value to here, then we can calculate XY, right? And that is your S. Again, you put it as a column vector, and corresponding the positions, the locations of each of the elements, they are corresponding to the S star. Then you can calculate S. And the S minus S star, you can get E. Right? So in this case, for each point, you have XY 2 values. And here you have 8 by 1 vector for S star. You also have 8 by 1 vector for S, and then the E is also 8 by 1. 8 by 1. All right. So then you calculate, you know how to calculate E already. You know how to calculate E already. And the next step is how to calculate the L. How to calculate the L, right? So we know what is the X dot and Y dot is equal to this, And also we know the capital X dot is equal to that, which means we can relate the X dot, capital X, Y, Z dot to the linear and angular velocities. And we put this equation back to here, then we have this equation that is the X dot and Y dot, which means the feature Jacobian. All right, so if we write it into the matrix format, and that is the matrix format. And in this case, because you know what is X and Y already, small x and small y already, and the only thing you didn't know is the Z, is a capital Z, which is the distance of depth between the camera to the object. And then you suppose you can measure that at the beginning, or suppose you give the value, estimate the value, then you can calculate this feature Jacobian. And again, this feature Jacobian is only for 1 point. You have 1, 2, 3, 4, 5, 6. You have 2 by 6 metrics. And then if you have 4 points, you just put them together as a column, then which means if you have 4 points, the Lx is a 8 by 6 matrix. You put it in different rows, then you have a complete XL. All right. And after you have the XL and E, you put it back to here. You put it back to here for the two equations, you can get the VC. VC is the velocity of the camera. You want the camera to go, and that is the control of your camera. All right, so that is the video, how to solve the video serving. And also, for solving the video serving, you need to have at least 3 points. You need to have at least 3 points, because the what you want to solve is the 6-dimensional velocity, and then your equations must be more than that, equal or more than that. So which means at least you need 3 points to solve it. But here we give example about 4 points, right? And here's example about activity 3. So do make sure you know how to calculate the camera velocity for the visual serving. And suppose you have an suppose you have a question in the final exam and asking you to calculate the camera velocity. Suppose. Then what you need to do to write that answer is you write the necessary equations. Please do write the necessary equations, and also calculate the values of the necessary variables. For example, you write the equations about how to calculate the feature Jacobian, how to calculate the pseudo inverse, and how to calculate the camera velocity. Those main equations. And after that, you need to calculate the necessary variables for the real case. For example, you have the equation about the feature Jacobian, and what's the real number of the feature Jacobian. So I'm not asking you to calculate it by hand. You can calculate it by using MATLAB, but you need to write the numbers on the exam paper. For example, you need to write the values, the values for the real case for the E and for the feature Jacobian L as well. You can calculate on the MATLAB and write the numbers. So write the true matrix of L and then write the true vector of E on the exam paper, and also S and S star. So please write the equations of those and also write the real numbers of that. And then you can calculate the pseudo inverse by using MATLAB, and you can also calculate the camera velocity by using MATLAB as well. But the thing is, you need to write the numbers you get for the necessary variables. All right, and also at last, I need to see the camera velocity, the real number camera velocity as well. All right, so process about solving that, and necessary equations and necessary numbers, necessary real numbers of the matrix and vectors, and then the final answer for that. All right, so that is visual serving. And after we introduce visual serving, we introduce the hand-eye calibration, because what we calculated is about the velocity of the camera, amount of the hand, right? But we want to control the end effector. We want to control the end effector of the robot. Then, which means we need to know the relative pose between the camera and the end effector. And then, after we calculate the velocity of the camera, then from the relative pose between the camera and end effector, you can calculate the velocity of the end effector you want to control. So that is why we need the hand-eye calibration. And how we can do that is we are solving the AX equal to XB problem. So for example, suppose this is the robot end effector, and this is the camera amount on it. And suppose we put a checkboard on it, so we can get, so when the camera and end effector moves, they move together, right? They move together, they move together from here to here. And from the checkboard, we can get the pose, we can get the relative pose between the camera position from here to here. We can get the relative pose, right? And also for the end effector, we can directly read the pose from the robot, right? So we can also get the relative pose between the move of the end effector. And we called it B and A respectively. And if we suppose the relative pose between the end effector and the camera as X, and it will never change. So which means here is X as well. Then which means if we want to calculate the pose of this end effector with respect to that camera, we can calculate as A times X. And we can also calculate that pose as X times B. Then we give an AX equal to XB problem, and there are some libraries to solve that problem. But the thing is, we have A from the end effectors, and we have B as well, which are from the camera relative pose. Then the only thing we didn't know is X. Then we can solve the problem, and X is the relative pose between the end effector and the camera. So that is hand-eye calibration. And there are some different configurations of the visual serving. Then, which means there are different hand-eye calibrations. For example, in this case, we are not mount the camera on the robot, but we mount the camera on a global case. But we put a checkboard onto the end effector. And we want to calculate the relative pose, the relative pose between the end effector to the checkboard. And how can we do? It is similar. So from the raw end effector, you can directly get the pose from the end effector, right? So you can directly get, if you move the end effector, then you can get the relative pose between the end effectors directly from the robot forward kinematics. And And because this checkboard move together with the end effector, then from the camera, you can get the relative pose of the between the checkboard from the camera. It's the camera extrinsic, right? So you can get the relative pose of the checkboard. And then after that is still an AX equal to XV problem. Then you can calculate the relative pose between the checkboard and the end effector. And to do make sure, so this is your homework after the video serving lecture. So do make sure you know how to do this hand-eye calibration. So this is another hand-eye calibration comparing to what we have to put the camera on the end effector. But this is a different one. All right, so try to make sure you know how to do it. All right, and there is another calibration we can also think about that in this case, which is the calibration between the global camera to the robot base. How to do that? Think about that. So it is quite easy because after you have this relative pose, and you know the relative pose between this one and that one, and you know the pose from here to base, and you also know the pose from here to there. Then you can directly guess the relative pose between the camera to the rotor base. All right, so do think about in this case. You know how to do the calibration and the calibration in the camera mounted on the hand effector. But how about this case? How about if you mount the camera in a global place and then you have an effector? So you have a pattern on the end effector, how to do this hand calibration. Right, do think about how to do it. All right, so that is all for today's lecture. And if you have any questions, please just post it to the chat, and then I will answer. I think I do have some questions now, so let's answer it one by one. All right, so wait a minute. Okay, so for the marks of the project, I will definitely give a breakdown for each of the deliverables. I will definitely give marks of each of the deliverables. But the thing is, I don't want to release it now because I'm afraid if some of the students have already get a higher marks, they will not care about the rest of deliverables or also the final exam. So I don't want to release it that early. And also, I will ask you opinion about if you just want to have a general mark of your project, or you want to have a specific one. So you can let me know which one do you prefer. But the default one is I will let you know for each of your deliverables there's a mark on it. I'm not quite sure if I can put it into the grid center, but I mean, I will definitely let you know about that. But if most of your opinion is about to have a total mark on the project, I'll definitely do that. But the thing is, I don't want to release the marks for the deliverables that early because I do want to make each of you perform quite well in the rest of the deliverables of the project and also the final exam. All right, so that is that question. And okay, so if you didn't get my emails asking why you're not submitting anything, then which means it is received. So it's hard for me to like reply like so many emails. But definitely you've received already. So don't worry too much about that. I've fully received your report. Okay. So any other questions on projects and on final exams or anything on the subject? So any questions, just make a chat. Just put your question in the chat. And also, I will definitely make some consultation times before the exam. But in my previous experiences, making it that early is not a good idea. So I always make like two or three consultation time, like for each of the week before the exam. But it seems like the students only count for the very last one. So that's why I want to make it a little bit later. So, but I will definitely make at least 2 consultation time. Then we can use the same the Zoom meeting address for that. And also for the final exam. So I will be online during the first hour and the last hour. The first hour and the last hour. I will be online on the Zoom, on the same address of the Zoom, in the first hour and the last hour. So if you do have questions, and please just ask me during the Zoom. All right, during the Zoom. So it is not that hurry. So read the question carefully, and if you have any questions, just ask me at the beginning. All right. And I should say, for the final exam, please answer the questions only by yourself, without others' help. Please, that is fair. That is fair for the other students. And as I said, it is not good to make the window that long, that 6 hours long, because if it's only 2 hours long, then you don't have time to help the others, right? And you don't have time to do something bad. But the thing is, that's a rule for from the university. I can't change. So what I have to do is I will design the questions that each of the questions the question for each of you, they may be slightly different to avoid this kind of thing happens. But as I said, I can't. It is not that easy to avoid this kind of thing happens without a formal exam, right? So that is the thing. And another thing is to make sure that the final exam is fair for all of the students. I will select some students to do some interview after the final exam, right? To make sure that the answer is from you. All right. So any questions on the everything on this subject? All right. So if there's no questions, I may end this this lecture. And then if you have any questions during the time, just send me an email. Okay. So the interview time will be after the final exam. It'll be after the final exam, and I'll try to make it within that week. I know some of you may have some other plans after the exam week. So I'll try to make it in the same week, but definitely after the exam. All right. So booking system. Okay. So you mean the booking system for the consultation or for the interview? Oh, for interview. Okay. So for interviews, it is selected. It's not for all of the students. I will contact you individually about the interview, and then I will not let the others know if you get interviewed or not. All right. Okay. So if all good, I will end this lecture, and I will look forward to listen to your presentations in the next lecture. All right. So thanks for choose the sensor control for mechatronic systems. And then this is not the end of the subject, and hopefully we will have a very, very wonderful presentation day in next week. All right, thank you very much. Thank you. So any questions, just send me an email. All right, so anytime, send me an email. All right, thank you guys. See you.